live? Are we? All right, we're live. Okay, so we're going to be talking today. Actually, this is the best thing. I wish that I could know when I was on camera and when I wasn't. And then it's out of focus. Oh, there we go. I'm going to turn out this light because I think it helps for the video. We're going to be talking about Chapter 5, which is least squares regression. I'm going to try to remember to post the videos after class. I think I created a new thing called videos. So, all right. So we're going to talk about OLS regression, which stands for ordinary least squares. OLS, ordinary least squares, okay? So it is a straight line. We are only going to worry about straight lines. We'll note that if they're not straight. Straight line that describes how the response variable y changes as the explanatory variable x changes. Okay? So remember, really chapter 5 is really a continuation of chapter 4, which means you can't forget, I mean you can, but you shouldn't forget from chapter 4. Okay? So the idea here is you're going to create a scatter plot. You're going to put your response variable y here, your explanatory variable x on this axis, okay? And, okay, so here's your scatter plot. Now, there's a lot of different lines. I could draw this line. I could draw this line. I could draw this line here, right? Which line is the best line? Okay? So when we use ordinary least squares regression, maybe I'll redraw this here. You can still see it here, okay? Maybe I'll make it a negative this time just to be different, okay? So we've got a bunch of dots here. Maybe these are negative. And so the ordinary least, oh, that's not even a very straight line, but pretend it's straight, okay? The idea here is, maybe I'll do this, okay? The idea here with ordinary least squares is you minimize the vertical distance, okay? So the idea here is, boy, those are big dots, okay? We are minimizing the vertical distance to the line, okay? That's what ordinary least squares regression does. Now, there are other methods that we could do. We could do the horizontal distance, okay? But that's not as good. You see that how that one looks a lot farther than it does in the vertical direction, okay? So we could do the horizontal direction, or we could also do what we call the orthogonal direction, the right angles. If I put right angles here, okay? So I could do that as well. So there are lots of different ways to create this line, okay? Now, if you guys really like statistics, I don't know if I'm teaching Math 2040 in the spring, but you should come to my Math 2040 class if I teach it, or somebody else's, okay? We will talk about why the vertical distance is the best method. So all I'm going to do is just say, trust me, it's the best method, okay? And so, yeah, that's ordinary least squares regression. So that's what we're going to be covering in chapter 5, okay? So now the question is, we need to find the equation of that line, okay? Now, in order to get in this class, you've all had Math 1010 or what I used to call Algebra 2 in high school. I don't think they call it Algebra 2 anymore, do they? Oh, they do? My kids are taking like secondary math. I don't know what it's called. But my daughter came to me today and she goes, I'm doing some tree today, Dad. Will you be home to help me? So I was like, oh yeah. My son's in calculus. He's like, I don't know. I'm like, I'm here. So anyway, so what is the, normally what form, when we're writing an equation of a line, what is the form that we usually use?
Y equals mx plus b.
Y equals mx plus b. Okay? What is that called?
Slope.
So that's called the slope point. Slope intercept. This is called slope intercept. Okay? And I'm going to maintain that because that's what you guys are used to. I believe in the book they have a slightly different form of this equation. Does anybody know? See who's been reading ahead? Somebody? Some people in my other class actually knew it. I was impressed. In the book, they have y equals a plus bx. So they kind of flip these around and they put the b in the wrong place. But anyway, this is what the book uses, okay? Nothing wrong with that, but I like this method better. And so all my formulas, you saw the formula sheet. Did you like that? Was that useful? Okay? So on my formula sheet, I'm going to stick with this form, okay? So in order to find the slope m equals r. What does r stand for?
It's correlation.
The what?
Correlation.
The correlation coefficient times s of y. What's that stand for? Standard deviation of y divided by the standard deviation of x. Okay? So that's how you're going to find the slope. To find the y-intercept b equals y bar minus m times x bar. Oh, I was going to fix that and I forgot. Okay, so here's what I would like to do. I want you guys to go ahead and open up Canvas. I'm going to turn this towards that. We're going to open up Excel. Actually, open up this here. So I've got a worksheet. If you go to assignments, unfortunately, I put the answers there already. I was going to erase it, but I forgot. So I'll have you guys erase this. We're going to go through the steps. The nice thing about having the answers there is I don't have to remember to put them up later. So if you go to the in-class worksheets here, just like this, and then worksheet 4.1. Okay. And then what I'd like you to do is, I can do this smaller, huge. We're going to erase all of this stuff, because we're going to do it here in a minute. This is the, these are the correct answers here. All right. So, a golfer has chosen to swing the ball on a 70-degree day with no wind. You want to see if there is a relationship between the club head speed, or how fast you swing, and the distance the ball goes in yards. Do you think there might be a relationship between that?
Yes.
Yeah, probably the faster you swing, the farther the ball's going to go, right? Okay, so that seems reasonable. Okay, so what's the first thing you should do when you have some data like this?
Draw a picture.
Yeah, what kind of a picture? Scatterplot, it's even up there for you. Normally I wouldn't do that to you. Yeah, so we're going to draw a scatter plot. Do you remember how to do that, Drew?
Of course.
Of course, you aced the test last week, so you're good. How do you do that? Sure hope you did. Me too.
Select your data.
Select your data. Do I include the title headings?
Yes.
Yes. Okay.
Insert.
Insert.
Charts.
Okay.
That first top left one.
Right here. The first top one. This one here.
Yeah, the one right below where your mouse is.
Okay. Perfect.
Yeah.
I didn't know if you wanted to do a bar chart there. I was like, no, I don't want to do that. Okay, so we've got our chart here. Is this a good looking chart? No, because you need to add your axis titles. How do you do that? Click the green plus sign, add your axis titles. What do I put down here, Clifton?
Speed.
Speed. And we probably ought to put miles per hour so we know what we're talking about, right? Speed. And over here we're going to put Jose.
Distance.
Distance. In what's the unit?
Yards.
Yards. That would be very helpful. Okay. And what do we want to put in for a title, Carson?
I have no idea. I've been trying to open it. Sorry.
What are we measuring?
Speed and distance.
Speed and distance on what happened? It's a 70-degree day. There's no wind. How about that? Okay? All right. So, Emma, does that make a straight line to you?
Not super straight.
Not super straight. Yeah, we could probably put a straight line in there. Okay. So this seems like straight line's a good fit. Would you say strong, moderate, weak, or no correlation?
Moderate.
Moderate. Okay. That's a good guess. All right. So there's a way to add the least squares regression. The nice thing about Excel is it adds the ordinary least squares regression line in here. So here's how you do that. If you pick a point, any point will do. It doesn't matter which one you pick. You right click and you say add trend line. Now, the one nice thing about Excel, it will do a lot more. You can click on these other ones. We're only going to worry about linear in our class, but you could do exponential, which doesn't look very different, or logarithmic, or polynomial, or power. The only one that looks really weird is the moving average. Okay? We're going with linear, so you can just leave that alone for now. Okay? So that looks pretty good. So that's the ordinary least squares regression line. Now we need to figure out how to put the equation for that line. So Maria, it must be your turn. Well, how do you think we find that equation?
So, sorry, what are we looking for?
I'm trying to find the equation of that line I just added to my graph.
So it would be the mx plus b, but
So we need to find the mx plus b, and how do we find the m?
r times
R times s of y over s of x. So what are some things that we should probably know? We need to know the correlation coefficient, right? And because I don't want to waste a lot of time on this, I'll let you use the cheater method on this test, okay? Because you've all proven, most of it, how to find the correlation coefficient. Do you remember how to find that, Kennedy? Equals?
Yeah, coral.
Coral. Okay. And then what?
And then you do the speed first, right?
Do the speed first,
So all in that, and then comma,
comma,
and then the yards.
and the yards. Very good. You did better than my class yesterday. That was good. Okay. So the correlation coefficient would be 0.938, and so you would say that was
Yes.
strong correlation, right? Okay. All right. What other information do I need, Rachel? To find the slope. What? What does S sub y stand for? Standard deviation. So you do know. Okay? So we need to find the standard deviation. How do I do such a thing? Am I going to make you do it the hard way anymore? Not until the final. Okay? So, do you remember the command?
I didn't hear you.
It's the
ST dub, right? Which one do I use?
just use the plain one or
Okay, the dot S,
.s.
dot S, or this one here.
Yeah.
Those are the exact same thing. Okay? Highlight your data. So I'm gonna copy that and paste that. Okay, so we've got a speed, the standard deviation speed is about 2.29 miles per hour. The distance is 7.74 yards, okay? All right, so we can now find the slope. So the slope M equals what, Arthur?
So that would be, you take, well, you have to calculate the standard deviation for all of the x and y values.
We just did. Rachel did that.
Okay, well, then you will divide the y value by x and times it by the correlation coefficient.
Okay, well, I'm gonna do the correlation coefficient first. R times what? Which standard deviation do I pick first?
Y.
Y, which is?
2.29.
No, that's the X.
Oh,
This is your X column, this is your Y column, right? This is your explanatory variable, this is your response variable. Okay?
so do you not have to do them like all separately then? Like when you do, when you're like computing with the correlation, you don't have to get the standard deviation for all of them.
So I did that already. Here, let's back up a second. Maybe we went too fast or something. But we went standard deviation, and this is my Y variable.
Oh, okay, never mind.
Did you miss that?
No, I just thought that I'm thinking of the long way of doing it for whatever reason.
yeah.
Yeah, we're good.
You like it better? All right. Okay. So we're back to here. So we're going to take our correlation coefficient. We're going to multiply that by
7.74.
7.74. We're going to divide that by
2.295.
Okay. So I got a slope of 3.1661. Buck, I haven't picked on you yet. What do we do next? You're Buck, aren't you?
Me?
Oh, are you not Buck?
No.
What's your name?
Colton.
Colton, sorry. Where's Buck today? Oh, Colton, sorry.
What was the question?
What do I do next? I just found the slope.
You gotta find the y-intercept b.
Gotta find the y-intercept b. And what other information do I need that I don't have?
Yes.
Do that.
You have the y bar and x bar.
We don't have the y or the x bar. So what do the y bar and x bar stand for? The mean. Okay, and how do I find that quickly, easily? What's the command?
Equals average.
Equals average. Thank you for speaking up, Carson. I know somebody else said it, but I didn't hear it. Okay? So if you like the whisper, and then you get mad because I don't hear you. I should whisper for Okay? All right, average, and then what do you say after you say average? Curse Bill Gates. Okay, all right, so the mean distance is 266.75 yards. The mean speed is 101, almost 102 miles per hour, okay? All right, so, is it Emma?
Yeah,
Emma, how do I find my y-intercept?
it's, so, y bar minus.
Y bar, which is?
Is that the 1.87?
No, that's not.
Oh.
Gotta make sure we know our x and our y variables.
2.6.
266.75. If we mix those up, it's gonna mess up everything, okay? Minus,
Minus, 3.166
the slope
times.
that we just found, okay? So if you get the slope wrong, you're gonna get this part wrong as well. Times
101.
101.875, that's your x bar, okay? All right, so Jose, I found the M and the B. What should the equation be for y equals mx plus b? We're just gonna write it down here.
So we
The
should.
regression equation is,
M,
so y equals,
so y equals 3.16
3.1661
times
times
x,
x plus
and then plus negative 55.796.
55.7966, right? Okay, so that is your regression equation for this. Okay, that's the best line to fit that data. Okay, now let me ask you another question. Do you think Excel can figure this out? You do have another question. Okay, and how many points are you going to get if you use that method? 0, but you will know if you got your question right. Okay, so here's how you do that. If you go back to here, you click on your straight line that you just saw here. If you go down to the bottom here, it says display equation on the chart. Look at that. Y equals 3.1661x minus 55.797. We put a plus in there, but you're always adding whatever that is, okay? Do you now, Kennedy, feel as smart as a computer?
Yeah.
Good, okay? Have you learned something today?
Yes.
I have succeeded as a teacher, okay, today.
When I click on the line, if I click on the side, it doesn't.
Let's see here.
Oh, wait. It just came up.
There you go. So the equation, right?
Oh, magic.
Okay?
Does that work?
Now, and of course, you can move that equation. Sometimes it's hard to read. I would like to put it above here so you can read it a little better. Okay? That's your regression equation. Isn't that cool?
Yeah.
Okay? Now, one of the things that we would like to know is, where I have to look at my thing again. How good, so we refer to that equation as our model. We just modeled our data, and that's the model it fits, okay? And so one thing that we would like to know, in the book, they call it the coefficient of variation. Okay, that's the official name. There is nobody that I know that calls it the coefficient of variation. Instead, they call it the R-squared value. What do you think R squared is? What's R? It's your correlation. So it's just simply your correlation coefficient squared. The R-squared value tells you the amount of variation explained by the model. Okay? So let's go back and let's figure out what our R-squared value is. Okay? So if I take my R squared equals my correlation coefficient, I'm going to simply square that value. Okay, so the correlation coefficient squared is 0.8815. So in this case, R squared equals 0.8815. Okay. So what percent of variation is explained by this model?
88%.
So 88% is explained. What is unexplained?
12%.
12%. 12% is unexplained. Okay, so let's go back here for just a moment. Let's look at our graph here. We'll close that. Okay, so we can see here, you can see we've got these two here. So one time I swung the golf club 100 miles per hour and it went 257 yards. Another time we swung it 100 miles an hour and it went 263 yards. Okay, why do you think, what are some reasons why it went farther or shorter one time than the other? Colton?
Maybe where you hit on the club face.
Maybe where I hit it on the club face. What else might explain it? Yes?
The wind direction?
Technically, there's no wind, but maybe there was a wind gust, right? Okay. What else? We're gonna find out if you guys are good golfers and know anything about golf. Arthur?
like, would you, like, I don't know, getting tired over time, like the time that you initially hit it?
Yeah, maybe we were tired the first time and we were just warming up. Okay, maybe. Except for it went the same speed, so that I don't know.
Maybe
I
you
don't
hit
think
it,
so, but what do you got, Colton?
depends on where the ball first hits, it could be like more grass, so it doesn't.
Oh,
go
yeah,
as
maybe
far.
there was a hard spot, or maybe you hit a rock, and it bounced farther, or bounced back.
Landed in the bunker.
What's that?
Landed in the bunker.
Maybe it
didn't
landed
go
in the
anywhere.
bunker one time, yeah. Bunker wouldn't let it go as far, right? Okay, so those are lots of things. So those are some of the lurking variables, I would say. Okay, so those sorts of things, maybe hit a wet spot and bounce forward or something. Okay, so there's 12% unexplained, but 88% is explained. So this seems like it's a pretty good model, right? Okay. All right. Now another question that I have here. Okay, according to this equation. Okay, let's pretend that I was swinging and then all of a sudden I went, oh, I missed it, I'm not going to hit it. Okay, I swung it at 0 miles per hour. According to this equation, how far would the ball go if I hit it at 0 miles per hour?
Negative 50.
It would go backwards 55.797 yards, right? Does that even make sense? Okay, but that's what the equation says, right? So what I want to point out here is this right here, okay? Prediction outside the range is risky. Okay? Now, when we talked about the range here, let's go back to, we're going to pretend that that's my golf data. Okay? So this is my miles per hour, and this is my yards. Okay? Now you guys can still see the equation because you got it on your sheet, on your spreadsheet here. What was the lowest speed I had on there? 99. And the highest speed? 105. Okay? Now, it's really good for those ranges. But, and maybe I could go with, say, 98 or 106, right? But if I go clear down to 0, it says the ball's going to go backwards, right? Or even if I went 10 miles an hour, the ball's still going to go backwards, right? According to the equation, okay? And so it's really good, and that's why, remember on the first test I told you I wanted the range, and the range was 99, 105. That's why I want you to know those endpoints, okay? Because it's really good to predict. You can follow that line and be able to predict how far it would go, okay? But it's not so good if maybe I hit it 80 miles per hour or 120 miles per hour. It wouldn't be so good, okay? One of my favorite examples is, let's say I had, let's say I had a growth chart here, okay? This is a person's age, and this is their height, okay? Well, you know that toddlers grow really fast, right? Okay? So maybe we've got something that looks like this, right? Maybe this is age 0 to, say, age 18, okay? And so you can see you've got a nice straight line here. What happens at age 18? Do you keep growing? As a general rule? Mr. David Robinson, okay? It's gonna arrow out like this, okay? So by the time you're age 50, you'd be like 9 feet tall, right? Okay, because if you're only using this range, look at that, you're gonna keep growing, okay? And so sometimes, and you never know, going back to the golf example, you know, if you hit the ball 200 miles an hour, it might blow up, you know, disintegrate, or you'll probably break your club, okay? If you hit it at 0, it's sure ain't going backwards, okay? So that's why we say prediction outside the range is risky. So some things to remember here. Yeah, we're still good. Things. Oh, actually, eraser. So that was one of the first things I wanted you to remember. Things to remember. Number one, prediction outside the range is risky. Number two, correlation / regression, since they're kind of related to each other, are strongly influenced by outliers. Okay? Now, we want to talk also a little bit about the difference between an outlier and an influential point. Okay? So let's say, for example, that I have some data that looks like this. Okay? Now, if I include it just like it is, you can see I can draw a straight line there, right? Pretty easily. What happens, and I'll pick a different color here. What happens if I have, say, an outlier here? Okay? What's going to happen with my correlation, my regression is it's going to draw the line away over there. So it's going to change the slope rather dramatically. Okay? Sorry, focus. Focus, I say. Okay. So it's going to change the line dramatically. So we would refer to this not only as an outlier, although it's funny because it's within the range of x values, right? And it's also within the range of the y values, but you can see that it's very different. Okay? So we would call this an outlier, and we would call it an influential point. Okay? Now, sometimes you may have two outliers, and maybe you'll have one over here, and it'll balance it out. Okay? So maybe these two will cancel each other out. You could also, in another case, okay, this was a case that we had, I think, did I tell you about the alligator movie we used to tell people to watch in my online class? It was like a 2-hour movie. It was really interesting. So here's the interesting thing, okay? So we've got some data that looks like this. In Africa, in the Sahara Desert, these archaeologists, or paleontologists, I guess they were, found a crocodile head, just the head. They didn't find the rest of the crocodile, only the head. The head on this crocodile was 6 feet long. Can you imagine? I'm 6 feet tall. Can you imagine a head of a crocodile that was as big as me? Holy crap. Okay? It was an outlier that they hope was up here. Okay? So this would be an outlier that's not influential. Okay, because the idea is it's probably still going to go through there. Okay? These 2 points here would be influential points because it would draw them towards them. But this, if it's in line, you'd still call it an outlier, but it would not be as influential as these other 2 points that we're kind of on. Okay? So what they did is they said, oh, we want to figure out how long this crocodile was, if it was like modern day crocodiles. So they measured all these crocodiles, and they measured their head length and they compared it to their body length, and they said, okay, so if this crocodile here is the same, has the same ratio, how long do you think that crocodile would be? Give me a guess, Jose. 50 feet, that was a little big. It was about 40 feet long. They actually made what they think it probably looked like. It filled the whole room. It was just huge. Okay? But they used regression for this sort of thing. And so the third thing that I want to point out here is that regression can be used for prediction. Okay, now what's the big caveat here, especially with the crocodile? Rule number one, right? Predicting outside the range is risky. So maybe it was just a short, stubby crocodile with all head and no body. I don't know. Yeah. So it's a little bit risky there. Okay. So anyway, since we're talking about crocodiles and bones, I don't know if you're going to be able to see this on my notes here. Oh, it's actually focused, kind of. You may not think this is funny, but I found this humorous. But I'm fun. That worked better than yesterday. Yesterday was out of focus. All right, so let's talk about the question of causation. We talked a little bit about this last time, but number one, strong relationship does not mean one causes the other. Okay? Number two, relationship between two variables is often influenced by lurking variables. Number three, the best evidence for causation comes from randomized experiments. Okay. Number four, relationship may be due to A, direct cause, B, common response, or C, confounding. Okay? Best example of confounding, do you remember the video I showed last Thursday about the ice cream and the polio? Okay? So the interesting thing about that, yeah, ice cream doesn't cause polio. But step 5, observed relationship can be used for prediction, even if not cause. Okay? So we could use ice cream sales and still predict the number of polio cases, even though ice cream has nothing to do with polio. Okay? And so that can be used. We can use the ratio of crocodile head of regular crocodiles to their body length to predict, hopefully, this super crocodile that was just ginormous. Which also means that Africa at one time, instead of being a desert, was a swamp. So you can see climate change right there. All right. Any questions you guys have for me? Okay, so I want to show a video. We're really good on time here. I want to show a video, but I don't want to get a copyright violation. So I'm going to end the stream for a moment. We'll show it here in class, and then we'll probably pick up with chapter 12. So we'll end this for now. Okay?